Now we'll see the derivation of logarithmic decrement. So for underdamped system, we have already derived that x is equal to m e raised to minus omega n zeta t sine omega dt plus sine. So we have seen that this is the amplitude part and this is the frequency part or direction part. Now we know that the logarithmic decrement delta, it is defined as ln of ratio of successive amplitude or log to the base e of ratio of successive amplitude. That is log of x1 by x2, log of x2 by x3, log of x3 by x4 and so on. So in place of x1, so this is the amplitude part. So m e raised to minus omega n zeta t. This is the time period which is required for the first cycle. For the second cycle, t is replaced by 2t. Then what will happen in this particular case? We can cancel out the value of m from the numerator as well as from the denominator. So what we're left with is ln of e raised to minus omega n zeta t divided by e raised to minus omega n zeta 2t. Now this is nothing but a raised to m divided by a raised to n, that is a raised to m minus n. But here already the minus term is there, it will go in the numerator and will become plus. So it is e raised to minus omega n zeta t plus omega n zeta 2t. So ultimately it is nothing but what? It is log to the base e of or ln of e raised to omega n zeta t, because here it is 2t and this is minus t, that is t. So this is the first form of this logarithmic decrement. So let us call this as equation 2 because first part is our definition part. So omega n zeta t, so this is log m raised to n, that is n log m. So this n term we have taken in front of the log, so this is log e to the base e, that is nothing but 1. So once again try to understand this. Log m raised to n is n log m, so here it will be e and this e will remain, so log e to the base e is 1. So delta is equal to omega n zeta t, because log e to the base e is 1. So this is our third part of the third representation of delta. Now we know that the damped frequency is given by omega d is equal to 2 pi f. So this is 2 pi multiplied by frequency is 1 upon time period. Now t will be equal to, so transfer this omega d on this side and t on this side, and now you can substitute the value of omega t, that is nothing but substitute this value in equation 3. So it is delta will be equal to omega n zeta 2 pi upon omega d, and now we can substitute the value of omega t. So in this step we can substitute that value, that is omega n square root of 1 minus zeta square. So you can cancel out omega n from numerator as well as from the denominator. So it is 2 pi zeta divided by square root of 1 minus zeta square. That is the another way of representing delta. Now the important part is this particular step. So we have to square this entire term. So squaring both the sides, so delta square will be equal to 4 pi square zeta square. Here square root will vanish, so it is only 1 minus zeta square. Transfer this 4 pi square term on this side, it will be in the denominator. So we are left with zeta square 1 minus. So transfer this 4 pi square term on this side. So it is zeta square divided by 1 minus zeta square. Now delta square divided by 4 pi square plus delta square is equal to zeta square divided by 1 minus zeta square plus zeta square. So what we have done on the left hand side as well as on the right hand side, we have added the numerator in the denominator. So this is the componendo and dividendo method. So numerator is delta square, which we have added in the denominator. Here numerator is zeta square, that is also added in the denominator, so that we can cancel out this zeta square from this side in the denominator. So we are having now delta square divided by 4 pi square plus delta square is equal to zeta square divided by 1. Only 1 will remain on this side. So ultimately zeta square will be equal to delta square divided by 4 pi square plus delta square. So zeta will be equal to square root of delta square is delta and square root of 4 pi square plus delta square. So this is our another way of representing the value of logarithmic decrement. Now we know that the ratio of successive amplitude is x1 upon x2 is equal to x2 upon x3 is equal to x3 upon x4 and so on. Suppose we consider the first two terms. So x2 multiplied by x2 cross multiply this. So it is x2 square will be equal to x1 x3. Now divide both the sides by x3 square. So this is the important step. So x2 square divided by x3 square will be equal to x1 x3 divided by x3 square. So x3 and x3 square, one x3 will remain in the denominator and here it will be x2 upon x3 whole bracket square. So we can say that x2 upon x3 will be equal to x1 upon x3, transfer this 2 on this side, it will be 1 by 2. So in general we can write down the expression as, so here x1 upon x2 is equal to x1 upon x3 raised to 1 by 2, because x2 upon x3 is same as x1 upon x2. The ratio of successive amplitude, that value, this ratio is remaining same. So in place of x2 upon x3 we can substitute x1 by x2. So we can say that delta is equal to, from equation 1 it is x1 upon x2, that is the ln of ratio of successive amplitude, but x1 upon x2 just now we have derived that it is x1 upon x3 raised to 1 by 2. Transfer log m raised to n is n log m, so 1 by 2 will come in front of log, so it is 1 by 2 log of x1 upon x3. And now you can see the relation between this 2 and this 3 term. So if n is equal to 3, then we can say that x1 upon x3, where n is equal to 3, you will have n minus 1 term, that is 2 over here. So it is 1 upon n minus 1. Or you can write down in the another way also. If you consider this as n, then here it will be n plus 1. For example, here it is 2 and here it is 3. So if this 2 is assumed as n, then here it will be n plus 1. So another form of logarithmic decrement is 1 upon n minus 1 ln of x1 upon x1, or you can say that 1 upon n log of x1 upon xn plus 1. Both of these forms there, they can be used while solving the example. So this is the representation of logarithmic decrement in various forms. So this is very useful in solving the examples on this particular damped vibration, free damped vibration system.